So in this video, we'll try to figure out the excess pressure inside a surface having two different radii of curvature. So let our surface look like this. This is one side of the surface. The other side may look like this. And if I complete the diagram, the whole surface is like this. This side has a different radii of curvature. Let's call that R1. And this side has another different radii of curvature. Let's call that R2. And this may be some liquid film, and the outside medium is some gaseous medium. Let that be air medium. So because of the property of surface tension, this liquid surface will try to contract, and therefore forces of surface tension will act along these edges. So let surface tension be T, and T is obviously the force per unit length as defined in surface tension. So T is the surface tension force, which is per unit length. So let's imagine first what is happening here. Surface tension forces are acting from this side and from this side, and also from this side and this side. The surface tension forces acting from this side and this side, first of all let's focus on that. They will not obviously be in the plane of paper, because the surface itself is curved. The surface tension forces from these sides will act in an inclined way but in the downward direction, and their horizontal components will cancel out and their vertical components will only add up. And if I look at this side and this side, because the surface is curved, the T forces will act like this and like this, and their horizontal components will cancel out and their vertical components will add up. So ultimately we will be left only with the vertical components of force. So let me first draw a T force here, T again being the force per unit length, and a T force here. And the angle subtended by this side at the center, let's call that alpha. So half of that angle will be alpha over 2. So let this angle be alpha over 2. And if I resolve T along this direction, I will get T cos alpha over 2, because this angle is alpha over 2. If angle between two sides is something, angle between their perpendiculars is also the same. This side is perpendicular to this and this is perpendicular to this. So this is T cos alpha over 2, and the downward component being T sin alpha over 2. Now notice one thing, I am dealing only with force per unit length. To get the force on the entire side, on this entire side, I will have to multiply it with the length of this side. You will have to notice that the T forces which are tangential to this side are actually perpendicular to this side. So the T forces that I have drawn here are not actually acting on this side, but they are acting on this side and this side, and they are acting in this way, and their vertical components will add up, while their horizontal components, that is this component, they will cancel each other out. So I will have to multiply these forces with this side. So to that end, let me try to make, this is difficult to do because this is a three-dimensional diagram. let this whole angle be beta, so half of it is obviously beta over 2, and let me say that the radius of curvature on this side, let me say that that is R2, and the radius of curvature on this side, let me say that is R1. So the length of this side is actually R2 beta. So to get the net force acting on this side, I will have to multiply T with R2 beta. So all these forces will actually get multiplied with R2 beta, because we are calculating the force on these sides and we are finding out their components, and we are seeing which components cancel each other out. So T, which is like this, is also multiplied with R2 beta, and this force T sine alpha over 2 also gets multiplied with R2 beta. And we can do the same thing for this side. T forces will act like this, and their vertical components will add up and their horizontal components will cancel each other out. So these components will actually cancel each other out and their vertical components will add up. These lines are actually meant to be perpendicular to the plane of paper and in the downward direction. So let us see, if this angle is beta over 2, I think, yeah, this angle will be beta over 2, because this side and this side, they are perpendicular, and these two sides are perpendicular. So this is T cos beta over 2 and this is T sine beta over 2. And we can do the same thing here. This will be T cos beta over 2, and the vertically downward component, that is this, will be T sine beta over 2. Now notice again, these forces that I have drawn them tangential to this side, but these forces, which are actually forces per unit length, they are acting per unit length on these sides. So this T force is actually like this, and this T force is actually like that, and their horizontal components will cancel out and their vertical components will get added. And again, these are only forces per unit length. The length that I will have to consider will be this side or this side, and the radius of curvature of this side being R1 and the angle subtended at the center being alpha. These forces per unit lengths will get multiplied with R1 alpha if I have to find out the net force on this side or on this side. So this gets multiplied with R1 alpha. Actually, all of these will get multiplied with R1 alpha. I will not write all of them out. So when I consider these two sides, the T forces act like this. Their horizontal components, which is this, and the same for this side, they will get cancelled out, and their vertical components, which are these components, will get added up. And for these two sides, the T forces, which are like this and this, like that means like this and like this, their horizontal components will get cancelled out, and their vertical components, which are these two components, they will get added up. So the net force that I am talking about here is this multiplied by 2 and this multiplied by 2. Why this multiplied by 2? Because this force comes from this side and also from this side. And same, why this multiplied by 2? Because this force comes from this side and also from that side. So if I add up the forces, so 2 times R1 alpha T sine beta over 2 have just taken this, multiplied it with 2 plus 2 times this R2 beta T sine alpha over 2. This will have to equal the excess pressure between these two sides multiplied by the area to get the force. So if the excess pressure is delta P, the sides are R1 alpha and R2 beta, so the area is R1 alpha times R2 beta. Note that we are considering alpha and beta to be small. If alpha and beta are small, then sine beta over 2 can be approximated as beta over 2, and the same for sine alpha over 2. It can be approximated as alpha over 2. So what we get is 2 R1 alpha T times beta over 2 plus 2 R2 beta T alpha over 2 equals to delta P R1 R2 alpha beta. Note that alpha beta is common in all the terms, so they will get cancelled out. The 2 here and the 2 here, the 2 here and the 2 here, they will get cancelled out. So I'll be left with R1T plus R2T equals to delta P R1 R2. So if I take T common, T times R1 plus R2 equals to delta P R1 R2. So if I write my final answer here, I am required to find out delta P, so I'll take R1 R2 to this side, and my final answer will be delta P equals T times 1 over R1 plus 1 over R2. So that ends this video.